Hello everyone. So today we are going to talk about one or the first machine learning model, and this is very useful. It is called a regression. So there are several types of regression also. So and like I had explained in my introductory video, what are the different kinds of machine learning models are there and how they can be used, where they can be used. So we'll be going a little deep into the regression part in this video. So again, we will be talking about two major type of regression, which is linear regression and logistic regression, which are the most common ones. But I'll also show you the implementation of both of these. But in this video, we'll be restricting only to the linear regression, and in the next video, I'll be covering the logistic regression. Okay, so let's first start with the introduction part. So regression is a type of supervised machine learning algorithm. So supervised machine learning algorithm, as I had explained earlier, it means that you already have some kind of information for your data. So whatever the input data that we'll be getting in the real scenario, so for that we already have some kind of data which have some values, either labels or numerical values for those, and that is why it is called supervised, because we have some kind of supervision for making my machine learn based on that the data that is already there. Okay, so but the difference from other machine learning algorithm and the regression is that here we are trying to predict a continuous numerical values, okay, instead of some kind of classes, which is again the most common one. So in other words, regression is used to model the relationship between a dependent variable and independent variable. So I'll show you the mathematical equation as well. So there will be different kind of features, and based on those features we try to predict some one kind of one value. So for example, predicting the price of a house, right? So predicting the price of a house, which is again a numerical or a continuous value, right? Number, it's not a class. So for that we consider different features such as the locality where the house is, or the number of rooms, bedrooms, number of bathrooms, or the total carpet area, right? Total number of floors it may have. So different kind of features will be considered to predict that price. So that is why it is called continuous numerical value. Okay, and so here dependent variable will be the price, and independent variable will be all these features that I just talked about. Linear regression typically aim to find a mathematical function that describes the relationship between independent and dependent variable. So basically we try to find a line that fits the data points. So data points, if we represent it into two-dimensional with the dots, and again I will see this, and that what we try to do is that we try to find the line that fits the data completely in the sense that it need not go through each of the data points, but the error should be minimum. Okay, because if goes through all the data points, then it is probably overfitting, and so there is concept of overfitting and underfitting. So I will not get too much deep into it, but overfitting means that model has learnt way too much based on the too many variables, or because of the less amount of data, and that it does not perform well in the testing. Okay, underfitting means that it has not learned at all because of a less number of features, or probably because of large size of the data. Okay, now so there are several example. Linear regression, for example, is a simple form of regression like I was just explaining, and the logistic regression is a type of regression used for binary classification problems, so where the dependent variable can only take two possible values. So the difference is that logistic regression also gives us a numerical value, like 0. 0.4, 0. 0.8, 0.9, something like this, but based on a threshold we convert it into a classification problem. Okay, so we'll be seeing both of these one after other. So let's first get into the linear regression. So linear regression is a statistical method used to model the relationship between dependent and independent. Like I said, it is called linear because the relationship between the variable is assumed to be linear or a straight line. What does it means is that, as you can see here, all the x's which are considered as a feature. So the how this is how a linear regression equation looks like, or this is how it is represented, where y is a dependent variable and all x1, x2, xn are the independent variable, as I have mentioned here also. So b0 is an intercept or a bias that is being introduced, and b1, b2, bn are the coefficients or the slopes. Okay, so that is why it is called linear, because as you can see, there is no degree to any of these variables. There is no square or square root or cube root or to the power n, right? So that is why it is linear in nature. Now, the goal of the linear regression is to find the best values for the slope and intercept. So intercept is basically this value, that how far it should be from the x-axis, whether it should cross this point. That means that if all these values, all the x's are 0, then how much will be the y, right? So that is what we call an intercept. And as you can see, all these red dots represent the data points. For example, if we take an example of sales of a television, right? So let's say if 50 units have a sales of something around this much, so this is how it is represented. And if we take, you see this perpendicular lines, right? So this shows that the distance between the best fit line that we are trying to predict. And this is again calculated using cost function. So if we see that if we take the root mean square or R2 values, so there are different matrices that we can use to calculate the loss function, or the accuracy of the model. So for that we do this. So the absolute differences will be calculated, and then it will be squared and then taken the root. And if the value is minimum, then we can say that it has been it is the best fit line. So let's look into the implementation part of it. Okay. So before going to that, there are a couple of things that why we should use it, and what are the pros and cons. So a couple of things that is there, that it is simple, right? Simplicity. Because of simplicity, linear regression is simple and easy to use, understand algorithm that requires minimal computational resource. Again, because of the linearity, it does not need high computational power. Interpretability, the coefficients of the linear regression model are easy to interpret and can provide insights into the relationship between the independent and dependent variable. Flexibility, linear regression can be used to model a wide range of relationship between independent and dependent variables, including linear, quadratic, and higher order polynomials. Good for predicting continuous values, like we have already discussed, that like prices or temperature values, right? This kind of things we can predict. Robustness, it is a robust algorithm because it can handle outlier and noise. So outliers I had talked about in my previous videos. Again, what are they and how and why should we handle it? So doing the EDA help us do that. Now the cons part, that it assumes linearity. So in real world it may not be true, that there may be, like I said, it can be, the dependent variable may be dependent on the square of the independent variable, right, or the cube of the independent variable, but it does not assume that. So that is called polynomial regression. So we may try to cover that also a little bit. But here, sensitive to outlier, it can be sensitive to outlier if it is not handled correctly, and which can have a significant impact. So that is why I have discussed earlier that outlier detection and handling is very important. But once it is handled, it performs very well. Overfitting, it can be prone to overfitting if the model is too complex and has too many independent variables. So either we try to reduce the number of independent variable, or maybe increase the size of the training data. Okay, now it assumes independence, that it does not consider that one variable or one feature can be dependent on other features, right? So there may be chances that the number of rooms of a house is dependent on the total carpet area, but it cannot consider that kind of factor. Limited to numerical data, it cannot handle categorical data, but if we can convert categorical information into the numerical format, then it can handle it. Okay, so now let's get into the implementation part. Okay, so here we will go through this implementation, which I have already ran. And here we'll see, just to save time because it videos gets extending. So we have first imported all the important libraries such as NumPy, Pandas, Matplotlib, SciPy, etc. So this is a data set for cars. Okay, so for cars we'll have some information, so we'll look into this. So here if you see, we will first plot a scatter plot, okay, in between the weight of the car and mpg, which is miles per gallon. So we are trying to predict how much miles it will be if it is related to the weight of the car, if there is a direct relation. Okay, so let's first plot this. So as you can see, there is this is the mile and this is the weight of the car. Okay, so we can see some of these points, data points. Now, a scatter plot shows a roughly linear relationship between weight and mpg, suggesting a linear regression model might work well. So we'll try to implement using the sklearn. So sklearn again is a scikit-learn library which I had discussed in my second video, which is again very important, and we'll be using this only. So here if you see, the idea is that first we'll load this linear regression model into one variable, initialize it, and then we'll train the model using the empty cars data, the data that we have, right? So here we are first defining what will be our x, which is weight, and what will be our y. As I said, it will be the dependent variable that we try to predict based on weight. Now this is again linear and univariate. So it is called univariate because there is only one variable involved in predicting the dependent variable, or univariate or simple linear regression we can call it. Okay, so after that we'll do the training. Okay, so check trained model y-intercept and coefficients. Okay, so the output above shows the model intercept and coefficient used to create the best fit line. In this case, y-intercept, which I had shown you in the diagram, what is the intercept, is said to be this much, 37, and the coefficient of the weight is -5. In other words, the model fit line can be expressed at like this. So if you remember the previous equation, y is equal to b0 plus b1 into x1, right? So since this is a univariate dependent on only one variable that we are trying to predict, this will be the equation. Okay, so so fit method basically identifies, gives you these two intercept values. Okay, intercept and coefficient. So that is why we are trying to do the fit. So it basically what it does is that it starts with some random values of this intercept and the coefficient, which is like b0 and b1, and then it will iterate, calculate the difference between the true value and the actual value, the value that it is predicting. Based on that, it will do multiple iteration and come to the minimize the cost function, like I had explained, that calculating the RMSE and all. So it will minimize that. So based on that, whatever the value that we are getting is this much. Okay, now so we can get a sense of how much of the variance is in the response variable is explained by the model using score. So this is the variance. Okay, the output of the score function for linear regression is r squared, a value that ranges from 0 to 1, which describes the proportion of variance in the response variable that is explained by the model. In this case, car weight explains roughly 75% of the variance in mpg. The R squared measure is based on the residuals difference between the model's predictor for each data point and the actual value for each data point. We can extract the model's residuals by making a prediction with the model on the data and then subtracting the actual value from each prediction. Okay, so this is just we are trying to do actual minus prediction, means the residuals, like I said, and this is being used to calculate R square value or root mean square value, right? And this gives us some idea of the accuracy of the model. So if I calculate 1 minus residuals by total, where residual is the sum of the square of the model residual, and total is the sum of the total of the difference between each data point and the mean of the data. We could calculate r squared by hand. So yeah, so this is how we can calculate, but there are pre-built packages also that we can do use to calculate. Now that we have a linear model, let's plot it in the graph and see how it fits. Okay, so again we are using the matplotlib to fit that line, and as you can see that here x axis is weight and y axis which we are trying to predict is mpg, miles per gallon, and again we are plotting this, right? So if you see, the line looks like a very good to what data we have. It may not be perfect, but it is kind of good. So regression line looks like a reasonable fit, and it follows our intuition. As car weight increases, we would expect a fuel economy to decline, right? Outlier can have a large influence, and so we'll see how outliers can impact our data, right? So we have talked about this earlier also, that one outlier can impact our data and thus the prediction or the model. So since the regression deal with minimizing the squared residual, large residual have a disproportionately large influence on the model. So plotting so what we'll do, we'll just create one outlier where miles per gallon is 50 and weight is 10. So it does not make much sense of 10 like sorry, the weight to be 10 where the miles will be so miles per gallon will be so high, right? But we are just creating this data just to bring an outlier in it. So if we plot this, it looks like this is the data, outlier data. Now if we do the calculate the coefficient and the intercept, so the lines become like this, which is very incorrect, right? The most of the data is in this sense, but we are predicting it to be this one because of this one outlier. So that is why it is very important to handle it. Although this is extreme contrived case, the plot above illustrate how much influence it can have. So here now in a well behaved linear regression model, we'd like to residuals to be roughly normally distributed. It is very important, like we had discussed, that is we'd like to roughly even spread of error above and below the regression line. We can investigate the normality of residuals with a QQ quantile plot. Make the QQ plot by passing the residuals to the stats function in the SciPy stats library. Okay, so as you can see, this is how it looks like. When residuals are normally distributed, they tend to lie along the straight line on the QQ plot. In this case, residuals appear to follow a slightly non-linear pattern. The residual are bowed a bit away from normality line on each end. This is an indication that a simple straight line might not be sufficient to fully describe the relationship between weight and MPG. After making model predictions, it is useful to have some kind of metric or to evaluate the model performed. Adjusted R square is one useful measure, okay, but it only applies to regression model itself. We'd like some universal evaluation metric that let us compare the performance of different types of model. RMSE is a common evaluation metric that I had talked about earlier for prediction involving real numbers. Root mean square error is the square root of the, again it is self-explanatory, right? If you recall, okay, so let's see, here this is how we are creating the RMSE. So RMSE is nothing but the square root of the mean of the difference between the targets and the predicted, and the square of it. Okay, so instead of defining our own RMSE, we can also use it from the sklearn, which is mean squared error. Directly we can use it. So now when calculating RMSE, it is coming to be 2.9. Now polynomial regression. So like we have seen that in a real scenario, it may not be any kind of dependent variable, may not be just dependent on one independent variable, right? There can be more than one. So for example, let's say in this case there may be power of the car, horsepower, right? Because if you have more power in the car, so if you have more power, then the fuel efficiency will decrease, right? Because it needs more fuel to generate that kind of power. So we'll be considering that also, but that is a multivariate Here we are. So here we are considering the polynomial regression. Here, if you see that there may be, like I had explained, that it may not be directly related to linearity. It may be dependent on the square of the feature, or the cube of the feature, or to nth power of it, right? So let's say if we are taking this weight of the car and the square of it, right? And then we are creating a one data frame. So here as you can see, we are again trying to fit this model, and then identify the intercept and coefficient. Then the model accuracy is coming out to be 81.9%, which is approximately 82%, which is better than the earlier. The output shows us that including the weight squared term appears to improve the model's performance, because the R squared increased from 0.75 to 81.9%. Okay. It should be noted, however, that adding a more variable to the linear regression can never cause R squared to decrease. So now let's plot this in the graph and see how does it look like. Now if you see, this is a polynomial graph raised to the power 2, and if we plot this, it looks like much better than the linear one, right? There is a curve here. The quadratic function seems to fit the data a little better than the linear one. Let's investigate further by using a new model to make prediction on the original data and check the root mean squared error. So now the root mean square error, if you remember, was 2.9 earlier. Now it is 2.5. Since the RMSE of the quadratic is lower than the old one, and the adjusted R square is higher, it is probably a better model, right? We do whatever, however, have to be careful about overfitting the training data. So here, if you see now, what we will be doing, we will be taking more variables here. So overfitting describes a situation where our model fits the data we use to create it too closely. Like I had explained, that if the best fit line passes through almost all the data points, then it's probably overfitting, right? And it is not good for our model, because it will perform well in the training, but it will perform poorly on our test data. Okay, so this is why we generally don't want to use training data to evaluate a model. It gives us a biased, usually overly optimized evaluation. One of the strengths of the first and second order linear regression is that they are so simple that they are unlikely to overfit data very much. The more complex the model we create, and the more freedom it has to fit the training, the greater the risk of we run of overfitting. For example, we could keep including more polynomial terms in our regression and achieve lower RMSE in the training, but this would almost so what we will try to do is that we will show you with the power 2, power 3 up to power 10, and see how it will perform, right? So if you see this is the intercept, and these are the coefficients for all these. The accuracy seems to be very high. Notice the R squared has increased substantially from our quadratic model. Let's plot the best fit line. Okay, so here if you see, the best fit line looks like something like this. So notice that the 10th order polynomial model curves wildly in some places to fit the training data, right? So just to cover this here, it is trying to cover each of these points, which may not be necessary, right? So it is because of the this much polynomial order, which is up to 10th that we have taken. It is trying to cover all of these. While this model happens to yield a closer fit to the training data, it will almost certainly fail to generalize well on new data, as it leads to absurd predictions such as car having less than 0 miles if it wakes more than 5000 lbs, right? So which is kind of incorrect. Now we'll look into the multilinear regression. So multilinear regression, like I said, that if we have more than one feature, so here we'll be considering weight and horsepower. So these two will be trying to predict miles per gallon based on these two features. So here this is the intercept that we are getting after the model dot fit, and these are the coefficient for these two variables, weight and the horsepower. Now the improved R squared score suggests a horsepower was a linear relationship with the miles per gallon. Let's investigate this with a plot. Okay, so our r square value is now 82. So if you see, it is scattered like this, which while the MPG does tend to decline with the horsepower, the relationship appears more curved than linear. So adding polynomial terms to our multiple regression model could yield a better fit. So now we are trying to combine both multilinearity as well as polynomial linearity. No, it won't be linearity but polynomial component by squaring both these terms, right? So if we do this, now we see the r squared to be 0.89 and RMSE is 1.9. So the new r square, the new r squared and the lower RMSE suggests that this is a better model than any we made previously, and we could we wouldn't be too concerned about overfitting. Okay, so this is all, guys, for linear regression, but we'll cover logistic regression in the next video, so stay tuned for that. And let me know, I know I'm just covering this in a very fast and very uh, kind of just walking you through these codes, but the reason for doing that is, first of all, I want to keep it simple and to like do not waste much time. But just let me know if you guys have more questions, I'll try to answer those. So thank you for watching. Bye.